computer and share screen. I'm not going to be able to see chat. So if somebody, is anyone on the Zoom as well? Yeah, can someone just log on and so like if there's a huge chat issue at some point, that way we'll know because I'll be sharing. Right. So can well, I can't see if the people can see online. Let's assume that the people online can see. Let's assume that it's recording and let's make a start. So I am Rohan Alexander. Welcome to the Toronto Data Workshop. And we are a weekly series of workshops that are really designed to focus on the data side of data science. Looks good. All right. Thanks, Sean. And so today's talk is very preliminary. I kind of regret publicizing it as much as I did. And so I'm very much looking forward to your critical comments and feedback on my thinking here. So I'm an assistant professor here in the Faculty of Information and the Department of Statistical Sciences. The main content of the talk is going to be this book, Telling Stories with Data, which is in draft form and freely available at tellingstorieswithdata.com. In terms of what I'm going to talk about today, talk about where sort of is data science right now, what are some of the problems that we're experiencing, where does it need to go, and then I'm going to walk through 2 or 3 ideas of my own as to how we can get there. I'm not like my PhD is in economic history, right? I'm not a statistician. I'm not an economist. I'm not a political scientist. I'm none of these things, right? I get to see a lot of these folks work, but I'm never an insider on any of these groups. And I've never worked as a data scientist, so very much keen for your comments. So what is data science? We had a research panel last week at Kenzie, Ontario, and Mark Daly, who's a CS professor out at Western, he said, you know, he doesn't really know what data science is, and he doesn't really care. He's not interested in what it is. And we've seen a lot of these data sciences institutes launch. And to a certain extent, data science seems to be, to a lot of these folks, whatever you would like it to be. It's a mechanism that enables us to get grant funding, a lot of it. And in that way, it might be good that it's not very well specified. From an academic perspective, there's been, you know, most books on data science do attempt to define it. So one of the earlier ones, so R for Data Science, Hadley's book, talks about raw data into understanding. This is Nick Horton's book, again, all about getting information from data. This is Lake and Peng, and so they've got a very long answer, which, you know, seems good. And then Tiffany Timber's brand new book sort of talks about generating insight from data. So there's something going on about data, but there's also something, my high school debate coach would be very upset if I defined something while using, you know, the bits that I was trying to define. So having data in the definition of data science is kind of a little bit, he would not be happy with that. So for right now, for this point in the talk, and we'll return to this, I'm just going to define it as humans measuring stuff, typically related to other humans, and using sophisticated averaging to explain and predict. And we'll get into a better definition at the end once we've explored this territory. So why do we care? Why do we care about this at all? We care about it because if data science is kind of nothing, then nobody has any ownership of it. So in statistics, we have some problems in statistics. Big names in statistics come and they tell us, you know, what they think, and then graduate students come in and they say, well, this is wrong, and that's how statistics progresses. But if data science is not part of any discipline, then how can that happen, right? CS is going to have criticism from one side, economics is going to have criticism from another side. And so from an academic perspective, we've seen the reproducibility crisis in the social sciences, which is now we're seeing moving into the computer sciences and physical sciences. We have absolutely no idea of the role of p-values in statistics, basically, as far as I can tell. Like, we know what a p-value is. When it was developed, it had a very specific purpose, but statistics is now so widely used that it's really hard to know exactly what it should be. And there's a data crisis in computer science. They finally understood that actually these data sets that they're training their big models on actually matter. And the more that they look into their data sets, the more issues that they find with it. So this kind of matters a lot. Michael, you'll interrupt me, won't you? If there's something. Okay, banter is good. And so this really matters. And it matters because I see my students going out and getting important jobs. So they go out and they get jobs in consulting companies, and they then give advice to hundreds of companies every year on the basis of their data science. They go and they work for the government, and they're determining policy. They go and they work for all sorts of places where they're using data science. And frankly, I really worry about the foundations. And so this is my attempt to go some way to solidifying these foundations. So it's 2022. If you're not starting with a workflow, then you're sort of missing out. But I define a new workflow for data science, and it's something along the lines of: we start with planning. We go to simulation. We go to acquire the data. We explore the data, and we share. And I've kind of stolen these bits and pieces from different disciplines. So you can see project management, architecture, they're very, very heavy on the planning. In statistics, we're kind of less so. We're kind of really keen to throw a model on things. In simulation is something that I've learned from hanging out with statisticians. It's less used in social sciences. So some of this is going to be really obvious to some of you. You're like, oh, of course we use simulation if you're a statistician. If you're a social scientist, that'll kind of be new to you. Acquiring, and so this is where, like, from a statistical perspective, we're thinking of sampling. But as data science has been increasingly used, we're seeing web scraping, and all of that needs to be transformed from the raw data that we get into a data that we can analyze. And so there's a huge blind spot in that data cleaning, data processing aspect. Exploring is EDA, so exploratory data analysis, and your typical linear models, and then sharing data sharing your conclusions, because having something that you believe doesn't make it true. It just makes you like a crank. Right? It makes you a crazy person shouting from the streets unless other people believe it. And this is something that we've really neglected across all of these fields. We have this workflow in because, as I said, everybody's got workflow in the year 2022. But what this really boils down to is what I would like us to do is to think an awful lot. I would like us to mostly read and write, and only sometimes code. And so that's really what it boils down to. And all of this is predicated upon 10 elements. I'm not going to go through all of these today. I'm just going to focus on a few, but I'm just saying that sort of we have this workflow, and it's very much the tip of the iceberg, and that is dependent on a bunch of core skills that we need to try and be sure that, like, if we were coming out with a data science degree, I would want key aspects of every student coming out of that, which would be all of these aspects. So there's a whole bunch of stuff that I could focus on depending on the audience. I mean, I should add R and Python into this, but Git and GitHub, I'll assume that most of you are somewhat comfortable with that. Quarto, which is the successor to R Markdown. And so this is what we're going to use to write our documents in. Data cleaning, data storage is going to be a different talk. And then writing and communication, again, another talk. So I'm not going to focus on those. What I'm going to do is I'm going to go home. I'm going to begin by talking about Australian elections. So by way of background, if you're used to the Canadian system, the Australian system is very similar. We've got a parliamentary democracy. You've got about 300-ish seats. We've got 151. there's two major parties, the Liberal Party, which is concerningly called, like, that's the Conservative Party, and the Labour Party, which is the equivalent of your Liberal Party. And like, let's just say that we're interested, we want to know like the number of seats that each party won, like, you know, typical data science question. Sure, how many seats did each win? So what we want to do is in this rethought data science, we want to start by planning. And so in this case, in order to answer our question, we're going to need two data sets. We're going to plan two aspects. We're going to need to plan what the data set should look like. And this will become obvious, like why we're doing this in a moment. And we want to plan what the final graph should look like. So like, what is the actual thing that we're trying to produce? What should that look like? So why are we going to do this? We do this for the same reason that a builder doesn't come over to your house and just start building a wall. And actually, like they step back, they plan it out. It ensures that we think about like where the wall should be going, what type of bricks we should be buying. We really want to think carefully about what we're doing. We want to really carefully consider our situation. So we see a lot of these really large AI models, right? They trained on one data set. We saw this in the Aries talk on Monday. They were trained on a data set of like Stanford students who tended to be like super white. And then they took it to the general population who are like 50% black. And it turned out that their AI model was like really bad at detecting cases. The details are like roughly that. If we're in industry, it stops us from worrying about too much, from needing to worry too much about scope creep, and it enables teams. So none of my students, they go out and they graduate, none of them work by themselves. All of them are embedded within teams, or they've got management. And so we really need to worry about that if we think about what is data science in academia. And sure, this is going to slow you down in the short term, but it's going to speed you up in the long term. And so a little bit of time spent here will pay dividends later on. So here's an example of what it could look like. For those of you on Zoom, I'm just going to restart the computer in here. Maybe not. So while it's restarting, let's turn it around. Okay, so here's like an example of what it could look like, and we're really like emphasizing the fact that it should just be really quick, really hands-on, and a lot of the value is in the doing of it, not in the end result. Okay, we're back. Okay, so then we turn to simulation, and we're going to simulate at this stage, okay, which is rather early for a statistics workflow. We're simulating at this stage because it forces us into the details. I really want to know which variables here should be classed as what type. I really want to know which one should be integers. I really want to know which should be factors. In computer science, we distinguish between two types of languages, static types and dynamic types. Static types are ones where we say this is a variable and it is an integer. All it can be is an integer and it can never be anything else. Dynamic types, like R, are ones where we say, well, this is an integer, like Rohan is an integer. Oh, but Rohan can also be a character vector. It can change. There is one study in computer science, and they looked at changing from a dynamically typed language to a statically typed language, and they found a reduction in bugs in something like 15%. So if we can get 15% reduction in our bugs, then that would be great. The other reason that we want to be forced into these details is because we are then going to use these features to define tests. And we'll see one example of those in a moment. Okay, so then we're going to move on to a second example, and this second example is running times. So pretend that we're going out for a run. The marathon time, the fastest ever marathon was just broken on the weekend. So we're gonna be interested in the relationship between your 5 kilometer time, which is like 3 miles if you're in North America, 5 kilometer time, and your marathon time. So a marathon is roughly 8 times as long as a 5 kilometer run, and so we might expect sort of an 8 times or a little bit over 8 times difference. So this is simulated data for 200 individuals. Okay, if I'm in stats 101, what I do is I'm given this data set, and I do simple linear regression with LM from base R, and that looks something like this. Okay, let's then say that there's some rain, right? So I don't know if it was raining in Berlin on the weekend, but we would expect that if it's raining, we're going to be a bit slower. So we move to two variable sort of situation. So we're going to have what's your 5 kilometer time, and is it raining or not? And again, if we're in Scott's class, then Scott would teach us to do multiple linear regression, again, maybe with LM from base R, and it's going to look something like this. And what we can do is we can be really explicit about the assumptions that we've made. And these are not statistical assumptions, right? There's whole textbooks that are like, distribution of your integers needs, distribution of your errors needs to be, X, Y, Z. Assumption around heteroscedastic, like these are not those assumptions. These are assumptions around something that's not quite statistics, but it's also not quite CS. It's like, well, we're going to assume that the class of what's raining is a factor, not an integer. We're going to assume that the inputs are 5 kilometer time, a marathon time, they're minutes, not hours. There's a whole bunch of assumptions that go into that. And typically, you and I, when we're running this sort of stuff, we think about all of these, and we're mentally going through it, and that's great, right? But if only I can believe it, and if only I can be sure, then that's, again, not really contributing to the confidence of others outside that we've done this all correctly. So what we want to do is we want to introduce code that'll do that for us. So just to go back to our first simple linear regression model, what we can do is we can write some code that checks first the class of these variables. So firstly, is marathon time in numeric, is 5 kilometer time in numeric, and is the number of variables, do we have 200 in there? So we know that we haven't accidentally dropped some variables. We haven't accidentally changed the classes. Then we can run our regression. And then at the end, what we might want to do is we want to check that the coefficients are kind of what we expected. And we can get this from our simulation because we've got to simulate something. So it might be as simple as saying, okay, well, we expect that the coefficient is not going to be less than 0, right? Like there's no way that it could ever be negative. And so if it is negative, then we really want to know about it. And this isn't going to be a problem when we only have one data set, right? Because there's only one data set, you run this thing once, it's fine. But as we think to going to pipelines and we have new data sets coming in all the time, every second, we really want to be sure that our estimates are sort of between 6 and 10, and that's based on our knowledge of the fact that a marathon is 8 times the length of a 5 kilometer. Right. Moving to the multiple regression stage, you might be thinking, well, surely there's like an easier way to do this than like what if I have hundreds of tests, right? So we can create whole R code chunks of tests. We call them, so in this case, we're going to save this as an R script that's called test class or R. And we're going to call this suite of tests, we're going to call this a check of classes. So in this case, all we're going to do is we're going to check the types here. So we're going to check that things are doubles that it should be and characters that it should be. We're going to test the observations. So check that there's 200 of them. So this is a very similar idea to before, but it's just separating out the code into a different R script. And then finally, we can check that our estimate of the coefficient is greater than 0 and less than 20. So we write all of these out in a separate script, and then for when we go to run our multiple linear regression, we call these things first, call these tests first, then we run it, and then we can test the outputs. Okay, and why is this better than before? So Lee and Peng, they say, look, the best data science always starts with the science, not the data. And I just think that that's like completely wrong. The best like data science is a cyclical process where we iterate between the data, the science, the data, the science, the data, the science. We're like, we're defining data very broadly, defining science very broadly. We don't start with one thing and then go to the other. Like, it's an iterative process, and that's why we need these tests, and that's why we need this all written down. There is a movement towards saying, okay, well, we should make everything open. We should make all our code and all of our data open. And I obviously strongly agree with that. But there are, some people have good reasons for not being able to share their data. And what I would like is if we can put some of these tests of their data into their code, which you can almost always share your code. Like, there's nothing proprietary about code in academia. Nobody's. Then we can share a little bit more, and we can have a little bit more confidence in these results, because we can see, okay, well, we know for a fact that they had all 200 observations. You may think that this is a trite example, but in economics, ahead of the financial crisis, and now 15 years ago, we had various analysis that was done, and it showed that if we contracted the economy, that would be the thing to do. It turned out that they accidentally dropped 3 countries, and if you added those 3 countries back in, you get the opposite result. So like, these small things actually do matter. And so this is just kind of like one way of pushing us forward towards that idealized situation where we can share a little bit. So having done that little exploration as to like how data science should change, I think that we're in a better position to be able to answer the question. Sorry, Michael. Oh, you should be able to unmute yourself.
Maybe you can't hear them.
Oh, maybe I can't hear them. Oh, they're muted. Sorry. Okay, well, we can come back in the Q&A. And so I think that it's something along the lines of, it's very much a process, right? It's just to ensure that I'm not using the word workflow. Oh, no, we use workflow. It's very much this process, right? And this is what we're going to teach students. We're teaching you a whole process. We're not teaching you statistics, LM. We're not teaching you, data cleaning. We're not teaching you. We're teaching you a whole process. And what we're interested in is your ability to be able to develop and apply an end-to-end workflow. So you're thinking of a problem, you're thinking of a question, you're going and you're gathering some data about it, you're organizing that, you're analyzing that, and you're writing it all up. And the difference between this and, say, like economics, political science, is that we're interested in this in and of itself. So some people would have been interested in that earlier, like Australian elections example, because they're interested in Australian elections. Like, a data scientist is not especially interested in Australian elections. A data scientist is interested in this process that allows us to analyze Australian elections better. That's not to say they're not interested in like the questions as well, but like that's the main focus. And that is what separates statistics from data science. In my mind, this is not the stuff that statisticians are typically interested in. So if we accept that like data science should be this separate discipline from statistics, then where do we need research, and what sort of questions do we need answered? So effective tests are a huge area. Like, you could obviously imagine that we could write an infinite number of tests for any one situation, right? That's obviously silly. We need a way of working out like what is an effective test compared with what is not an effective test. And there's very little work that's gone into testing in data science in this context. We need to know what is going on at the data cleaning preparation stage. For a long time, this has just been this black box, and we just assumed a clean data set. We really need to open this up, and we need to explore like how much of what is happening in there is affecting the analysis. Is it all being, are all of our conclusions being created in that stage? Names. If you look at any data sets, even ones that are for very similar purposes, they all have very crazy names. Okay, very different names. What we need to do is work out, this is the same situation as it was in biology, like 250 years ago, right? All the animals have different names. Then they come in, now we've got like, binomial, 2 Latin names, it's all good. We all agree like a tiger is a tiger. And the reason that's important is that it makes you more efficient, because I can say, look, a tiger, and you can be like, okay, I should run. Whereas if I say, hey, look, DS, you don't know like if DS is of interest to you, like you're interested in, public health stuff, right? You don't know, is it women, is it men, is it, we need some sort of, we need to get better at naming. The machine learning revolution was being promised for a long time, and basically it turns out to be mostly snake oil. We need to know like what is happening here. It's really good at prediction, but like it turns out that the prediction aspects were not. We need to work out like what is happening with this prediction versus inference idea in the machine learning revolution. Data science, even if it is its own discipline, still has constituent parts. So this is CS, statistics, engineering, economics, all the rest of them. But what is the relationship with them? Right now, I started with like, data science institutes and all of those. And these are typically, they'll get bits and pieces of people from all of those different departments, and they'll bring it together under the one roof, and they'll say, look, you are a computer scientist, you are an economist, but you're also a data scientist, and that's great. But like, what does the relationship actually look like between those different bits? How do we teach data science? So there's basically, as far as I can tell, there is now agreement as to what we teach in data science. We teach Git, we teach GitHub, we teach SQL, we teach R, we teach Python, we teach some stats, we teach some sampling, and a little bit extra. Like there's basic agreement as to what goes into data science 101. But we have no idea how to teach it. Like how do we teach SQL? How do we teach Git and GitHub? There's very little evidence-based analysis of all this. And finally, what is the relationship between what is industry and what is academia looking like? So those are my thoughts. If you'd like to look at the book, then it's Telling Stories of Data. And if you'd like to provide any sort of reviews or areas that need to be improved, I'd deeply appreciate that. But very happy to take your questions.